We're going to start our problem with a specific triangle, such that its sides are in a 2-to-1 relation, as you can see on the sketch. Now, from the apex of this triangle, we will pull an angular bisector with the length of 2. And this bisector bisects the upper angle into two 60-degree angles. Now, the question is, can we somehow calculate the length of the base of this triangle? This awesome problem was sent to me by my subscriber Marian. So thank you so much for the wonderful suggestion. And if you guys want to try this out for yourself, you can pause the video right now and then come back and check my solution. Alright, so let's solve this problem together. So, before we start, I'm going to label all the vertices of our triangle as A, B, and C, and I will label the intersection point between our angular bisector and the base of the triangle as D. Now, in order to solve this problem, we're first going to take a look at the angle BDC, and I'm going to label this angle as alpha. Now, this means that the remaining angle ADC on the line AB must be equal to 180 degrees minus alpha, since this is the supplementary angle for the angle alpha. Now, let's have a look at the triangle DBC, and let's use a little bit of trigonometry. To be precise, we will use the law of sines. If you don't remember this law, it applies to any triangle, and it states that in any triangle, the relation between the side and the sine of the opposite angle always remains the same. So we're going to use this on our triangle CBD. We're going to use it on the side X, and the opposite angle will be alpha, and on the side DB, whose opposite angle will be 60-degree angle. Now we're just going to rearrange this a little bit in terms of dB and get the following. Alright, so now let's take a look at the other triangle, ADC. And we're going to use the law of sines once again. This time for the line 2x, whose opposite angle will be 180 degrees minus alpha, and the side AD, whose opposite angle will be 60-degree angle. But this time, before rearranging, we're going to take a look at the sine of 180 degrees minus alpha. This is actually the sine of the supplementary angle, and it is always the same as the sine of the original angle. So sine of 180 degrees minus alpha is equal to the sine of alpha. Now we're going to do some rearranging once again, and we will write our equation in terms of AD. Now we have those two equations, and we're just going to find the relation between dB and AD. Then we will do some cancellations, and afterwards we will get that dB over AD equals 1 over 2, which means that AD is 2 times the value of dB. And this is really important, because now on our sketch on the left we can do some simplifications. We can say that the line dB has the length of y, which means that the line AD must have the length of 2y. Alright, so let's clear our sketch a little bit. And for the second part of our problem, we will use another famous trigonometry relation, and that is the law of cosines. Now, if you forgot about this law, it states that the square of any side of any triangle equals to the sum of the squares of the two opposite sides minus 2 times the product of those two sides times the cosine in between those two sides. And we're going to use this law on our triangle DBC. So we're going to say that the line y squared equals to the sum of the squares of the line of 2 and x minus 2 times their value times the cosine, which is opposite to the line y, and this is the cosine of our 60-degree angle. Now we're just going to work through this a little bit, and we know that the cosine of 60 is 1 over 2, so after some simplifications we will get the following. Now let's have a look at our other triangle, ADC. And let's use the law of cosines for the line AD, which has the length of 2y. If we do this in the same way as before, we will get the following. Now we're going to put everything on a square, and we're going to use the fact that cosine of 60 degrees is 1/2, and after simplification, we will get the following equation. Now we're going to simplify our sketch and we're going to save our two equations, and we're just going to solve them by using the system of equations. I know that this maybe looks a little bit terrifying, but actually it's quite simple. We're just going to expand the first equation by 4 and get the following. Now from here we know that both of those equations are equal to 4y squared, so both of them are equal to each other. Now we can cancel 4x squared on both sides of the equation, and we will rearrange our terms so that unknowns are on the left and the known values are on the right, and we will get that 4x equals 12, which means that x equals 3. Alright, so now we're going to take this value of x and implement it into our first equation in order to get the value of y. If we do this, we will get the following. Now we're just going to work through this simple algebra and finally get that y squared equals 7, which means that y equals square root of 7. And remember, we're looking for the length of the line AB, which is actually the base of our triangle. And this line consists out of segments with the length 2y and y, which means that this line has the length of 3y. Now we will just substitute the value of y and get that our wanted length equals 3 square root of 7, and this is our solution. Well, I really hope you guys enjoyed this interesting problem. If you did, please do not hesitate to leave a like or subscribe to the channel for more content like this. Of course, if you found another way to solve this problem, please write it down in the comment section as you always do. And if you know a person who loves problems like this, please share this video with them. And until next time, see you guys and take care.